Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to apply Newton's laws with a problem involving some friction, and also how to couple that with studying the motion of an object. So what we're looking at here, we're looking at this inclined plane here, 25 degrees at the horizontal. We've got this object that's going to start here at what I'm calling position 1. And my question, or what we're going to try to figure out, is this. Given frictional coefficients of 0.1 and 0.15, we're going to try to calculate the delta t, how long it's going to take this object to get here from position 1 to the bottom, position 2. Right. Now for starters, maybe a quick little review about frictional coefficients. So remember, the frictional force is equal to the coefficient of friction times the normal. But this has two different possibilities here as far as the frictional coefficient is concerned. You have what's called the static coefficient of friction, typically is called mu sub s here, and this tells you the maximum possible frictional force. So in this problem, the maximum possible frictional force is going to equal the coefficient of static friction times the normal force. Right? You also have what's called a sliding coefficient of friction, typically called mu sub k. And this is what you use when you're trying to calculate a sliding frictional force. So your sliding frictional force is equal to the coefficient of kinetic friction times the normal force. So that's what these things are about here. Now, I didn't actually list which one's which. When I give exams, I expect people to know which one's which. Static coefficients of friction are always bigger than sliding coefficients of friction. So given these two coefficients of friction, this one must be the static coefficient and this one must be the kinetic coefficient or sliding coefficient of friction. Now, as we start thinking about this problem, an important thing to realize is this. It's conceivable that this object is just going to sit here. I went ahead and drew a second picture assuming it's going to get to the bottom, but perhaps there is enough friction to keep this object sitting here, in which case this time we would say is infinite. So before we even move on, we really should kind of explore that and make sure this thing is actually going to accelerate. So what I'm going to do here is I'm going to start with a free body diagram. I like my little tool here for drawing these free bodies. All right, and I'm going to draw a free body right at this position. I'm going to go ahead and draw some force vectors here. So we got a gravitational force acts down on this object, right, and that one's equal to mg. All right, surface and contact. So along here we're going to have a normal force. Now where we put that, let's see, doesn't really matter. We can put it anywhere along this line here. All right, we want this to make a right angle, so let me just let's see here. I think that'd be 65, yeah. And again, that normal can act anywhere along this line. So I'm going to go ahead and draw that normal force right here. We also have a frictional force acting at this surface. So I'm going to go ahead and put a force vector in for that. And that force acts right along this surface here. So I'm going to go ahead and put that force vector in. Those are the only forces that I imagine here acting on this object. Remember, forces come in two types, field and contact. The gravitational force is the only field force acting in this problem. The other forces are from direct physical contact. So make sure that I get that normal, whoops, a little easier to see the arrowhead there. Right, so we have direct physical contact here. We typically divide forces along contacts into two types: a component perpendicular that we call the normal, a component tangential that we call the frictional force. Now, it's not too tough to show that if this is 25 degrees, this angle right here also must be 25 degrees, and that's because this one and this one add to 90. I believe that'll make that 65, but from here to here is 90, and from here to here is 65. So that's going to make that one 25 degrees. Now, when we start writing equations, remember Captain Rod's rule of thumb: identify the acceleration direction, call that positive. The only possible acceleration direction for this is down and to the left. It's either going to accelerate down and to the left or it's not going to accelerate at all. So before I do anything, I'm going to put a coordinate system into this problem, following my standard rules of thumb here. Let's see, where should I put this? I'll put it right there. So I'm going to call that the x direction. Right? And then that's going to be the y direction in my problem, right? So x, y. Now, before we even write our Newton's second law equations, we're going to do kind of a comparison here of the frictional force and the gravitational force. If we think about what's happening in the x direction, the frictional force is basically trying to hold this thing still. However, the mg has components that are along the y-axis and x-axis. So I'm going to go ahead and draw those components in red. And I think what I'll do is draw them like this. So what I'm going to do right now is draw the mg in component form. So again, this black vector has a component this way. And a component this way. Boom, boom. Now, this is the component of the gravitational force that's in the x direction. This is the component of the gravitational force that's in the y direction, right? These aren't extra forces acting on the free body. I could have also drawn them like down into the right and then over. You can draw them either way, it doesn't matter. I chose to go this way just so I didn't overlap my normal force there. Now, in this triangle right here, the hypotenuse is the gravitational force, mg. And this angle right here, I believe, is a 25-degree angle because these two lines are parallel. So that 25-degree angle is that one right there in that picture. So mgx, that's what I would call this. That's the component of the gravitational force in the x direction, is equal to mg sine 25. All right, now we're going to take a look at that frictional force. The frictional force is equal to the coefficient of friction times the normal. So when dealing with the frictional force, we're going to need the normal force. We can get the normal from our free body by sum of all forces in the y direction equals 0. Now, it's important to realize why 0. The acceleration of this box is definitely down and left. It does not have a y component. So if we sum forces along this axis right here, they have to add to 0. So when I look at my free body, I've got the normal acting in that direction. So I'll put plus n. We've got a gravitational force component here, this one, that acts in the y direction. Now, I've got plus y up and left, and this force points down and right, so I'm going to go ahead and put minus mg. Now I want this component of it, the hypotenuse is mg. This component is going to be mg cosine 25 because it's adjacent to the 25-degree angle. And as I look at this free body, those are the only forces that act along this axis here, the normal and the mg cosine 25. So this sums to 0. So the normal force is equal to mg cosine 25 degrees. All right, so we can say that the frictional force is equal to the coefficient of friction times the normal, which is mg cosine 25. So now the million-dollar question is, is this thing going to start sliding or not? We need to determine that. And the reason we need to determine that is we need to determine if this coefficient of friction is relevant or not. Is it going to start sliding? So I'm just going to do a quick comparison. In my picture, this is the force component that's trying to slide that thing down the box. That's the mg sine 25. And the frictional force, right, I've got an expression for that right here, is coefficient of friction times mg cosine 25. So the million-dollar question is, which one of these is larger? if this force is larger than this, it's guaranteed to slide down the incline. Now, we don't have a mass, but that's okay. You notice it's an m in both sides, so I'm just going to leave that there. Actually, the mg is the same in both sides. And I'm just going to compare sine 25 to cosine 25 times the coefficient of friction. So the sine of 25 degrees is 0.42. Right? And then the cosine of 25 degrees is 0.9, but that needs to be multiplied by the coefficient of friction. Now, what I'm interested in here is the maximum possible frictional force. So I'm going to compare that to 0.15 cosine 25 mg. And I get 0.13 out of this. It's this right-hand side. I end up with 14 mg. So when I compare 0.42 mg to 0.14 mg, this one obviously is bigger. So in my picture, that means this force component is actually larger than that frictional force. That guarantees this thing is going to start sliding down the incline. And now I know that the relevant coefficient of friction is the sliding coefficient of friction. So now I can go ahead and look for the acceleration of this object. And I would do that by sum of all forces in the x direction equals ma. Down and left is what I'm calling positive. You know, my standard rule of thumb, identify the acceleration direction, call that positive. This object is going to be accelerating right along this axis in the positive x direction. So I look at my free body now, and I'm looking for forces in the what I'm calling the x direction. So there's one right there, opposite the 25-degree angle. So that's going to equal mg sine 25. Here's another force. I'll just put minus f for now along the x-axis here. Minus because this is up and right and I've got down and left positive. And that's it. The normal does not have an x component, so this sum is equal to ma. All right, next step. mg sine 25 minus the frictional force, which can be written coefficient of kinetic friction times the normal. The coefficient of kinetic friction is 0.1, so I'm going to go ahead and just put minus 0.1, right, times the normal force. And the normal, we already found that from summing forces in the y direction here. The normal is equal to mg cosine 25. So there's minus my frictional force equals ma. Now, as I glance along this, I notice that the mass is the same in each term. There's an m here, here, and here, and that means we can divide it out. So the acceleration is going to equal g sine 25 minus 0.1 cosine 25. Now, numerically, again, g, because I'm working in metric units, this is going to be 9.8 meter per second squared. To save myself some room, I'm not going to bother copying that, but 9.8 times the sine of 25 degrees minus 0.1 times the cosine of 25 degrees. You can just type that in just the way you heard it there. I get 4.05 meter per second squared for the acceleration. All right. So 4.05 meter per second squared. I think we're in good shape here. So now we know the acceleration of this object as it accelerates down the incline. Next is to study the motion of the problem. So to do that now, I'm going to go ahead and use this same set of coordinates here. However, I'm going to make one little change. I'm going to move that set of coordinates so that at t equals 0, x is 0. So I can either maybe put it right on top of this, or even right here would be just fine. But the important thing is I need this coordinate system to be set in such a way that at t equals 0, x is 0. So now it is. So now I'm going to think about what the velocity graph would look like. So when you study motion, velocity is very, very, very important. So I usually start with that. What is the velocity doing? So I'm going to go ahead and draw a velocity graph. I'll just draw it right here. All right, so I'm going to do is just a quick graph of velocity against time. All right, T, V. Now, keep in mind at t equals 0, this thing starts from rest. So that first point is going to be here, and the acceleration is 4.05 meter per second squared, but you'll notice this is not a function, this is constant. And when we have constant acceleration, that's going to give us a linear velocity graph. So if we were just to sketch a quick graph of velocity against time, it's going to look something like this. I don't know the time for it to get to the bottom, and we don't know this either. We don't know the final velocity, but we do know that it's equal to acceleration times time. So this is going to be 4.05 t, and I'm just going to put a little note, consistent units. This is coming from the fact that acceleration is the slope of a velocity curve. So the equation for this line can be written v equals acceleration times t plus some intercept, but the intercept is 0. I can see that from my graph. All right, next step. The area under this curve, this area right here, is going to give the change in position, the delta x. And that's going to equal, because this is a triangular area, 1/2 t times whatever this distance is, which can be written 4.05 t. So now I'm going to go ahead and put numbers in. I can observe from the problem that the delta x is 4 meters. So this is going to be 4 meters equals, let's see, 4.05, I'll just leave that, 4.05 over 2 t squared. And I guess, to be consistent here, if I'm going to leave units off, I should leave them off everywhere. Either put them in everywhere or leave them off everywhere, but don't do half and half. All right, so this was 4.05 meters equals, all right, 4.05 over 2. This would actually have units of 1 over second squared, all right, times t squared. So when we solve this for t, whoops, let me go back. This was, let me talk units just for a moment. This was 4 meters. This term would have units of meter over second squared, and then we would solve that for t. It'll come out in seconds. So the t is going to be 4 times 2 divided by 4.05, and then square rooted. I got 1.4 seconds out of that. And while we're at it, although it didn't ask for it in the problem, at position 2, this object would have a velocity in that direction, which I would call v2 or v final, and we can now get that right from this function. I'll just do it right here. Our final velocity is going to be 4.05, and again, that'll have units of meter per second squared times t, 1.4 seconds. So our v final is going to be about 5.7 meter per second. All right, so let me kind of highlight this problem, go over the important parts here. First of all, the free body. That's probably the most important part. We have an mg down, surface and contact, so we have a normal and potentially a frictional force. If this were a frictionless problem, if this were a very well-oiled surface or something, we'd be tempted to leave that one off, but it's not. There were frictional coefficients mentioned in the problem. Before you can proceed, you really have to determine whether or not this thing is going to start accelerating or not. And the way we do that is we compare the maximum possible frictional force to the force component that's in the other direction. And that's what I did right in this region here. mg sine 25 is that force component. Think of it like this. It's the force component trying to accelerate this down the incline. The frictional force can be written, normal times the coefficient of friction. So whenever you're dealing with friction, you typically need the normal. You get the normal by summing forces in the direction of the normal. That's what I did right here. So in this problem, the normal was equal to mg cosine 25. So the million-dollar comparison here is the mg sine 25 against the coefficient of friction times mg cosine 25. Now we don't have an m, but the mg is constant on both sides. So in this problem, it's just a matter of comparing the sine 25 to the coefficient of friction times cosine 25. This force obviously larger. Once we know that, then we know the coefficient of friction to use is the 0.1, because now we know it's going to be sliding. That allows us to write this equation. That's a really important equation here for this problem. Summing forces in the direction of the acceleration. So looking at my free body, that's the vector sum of this force and this one. Now, when I drew these forces, I wasn't sure which one's larger. In reality, we know that this one's larger. We could go back and shorten this. I'm just pointing out that these forces are not proportionally correct in the free body. This one actually has to be a little larger than this one, but I'm not going to bother changing that now. We write our Newton's second law equation, find the acceleration. Then, what do we do with that? The acceleration is the slope of a velocity graph, so that's what allows us to graph velocity against time. This goes through the origin because this started from rest. It's linear because the acceleration is constant. Then we can find the equation of this line because we know the acceleration is 4.05 meters per second squared, so that's the slope, and there's no intercept. Then we set the area under this curve equal to the distance, or the delta x, that we know that this box is going to do, going from position 1 to position 2. That's what allowed us to solve for t. You can then take that t back into this to find v final. So I hope this video helps. I hope it's a good demonstration of how to draw free bodies, how to incorporate friction, and how to study the motion of a system. All right, everybody have a great day.